Are you detail-oriented? Do you want to know how things work? Enjoy solving problems? Then a career in STEM might interest you. The STEM, or Science, Technology, Engineering, and Mathematics Career Cluster, focuses on planning, managing, and providing scientific research and professional and technical services, including laboratory and testing services and research and development services. STEM workers do scientific research in laboratories or the field. Others plan or design products and systems, or you might support scientists, mathematicians, or engineers as they do their work. You might oversee the construction of roads, develop systems to prevent diseases, or help engineers do research and read blueprints. There are over 60 careers across 2 pathways in the STEM career cluster. Those pathways are engineering and technology, science and mathematics.
I've been interested in life sciences my whole life. My dad is a veterinarian, and I grew up going on emergency calls with him and got interested that way. Science was a natural choice for me whenever I went into college. Ended up spending a lot of time doing research in different laboratories, and whenever I moved back to Southern Illinois, I was lucky enough to get a position teaching part-time here at the college and got to use science again and have really enjoyed teaching science to students. It's a wonderful thing to be able to share that.
For myself, I got my start teaching science working at education centers in some locations out west, and that really increased my passion for talking about the sciences and really bringing that material to life with different experiments and demos and things of that nature. And I think more than anything, just a love for the outdoors and trying to come to a better understanding of kind of how a lot of the rock formations and things that I was seeing in different places across the US, how those formed and what processes led to their formation. On the physical science side, you deal with a pretty broad range of things. So if you're looking at something like engineering within the physics area, that could be something with mechanical or aeronautical engineering where you're designing bridges or designing different things for even NASA or Boeing or something along those lines. In my key area, which is geology, a typical day is spent outdoors, exploring maybe something within oil and gas, working for an environmental agency and doing an evaluation of an environmental cleanup site. So it can vary quite a lot within the physical science area.
In the life sciences area, a typical day might be working in public health. Certainly with the coronavirus pandemic, there's been a lot of interest in epidemiology and virology and even vaccine science. So that's something that has been at the forefront of our news and our concerns over the last year. It also involves education. So life scientists might spend time educating people about the environment or educating them about endangered species. But a lot of life scientists spend a lot of time in research, and you can research just about anything in any field whenever it comes to the life sciences and spend your whole career investigating some small niche of our beautiful and complex world. I think a life scientist needs to have a very inquiring mind, and they need to be willing to kind of set their teeth on a problem and then hang on until they get it solved. So I think that persistence is really important, because many times whenever you're chasing down a solution to a problem, you spend a lot of time failing, and you may fail 20 times before you have any successes. So I think that persistence and that ability to stick with it is very important. And then also the attention to detail, and sometimes to think outside the box, to see what no one else has seen.
Well, I would say, I think, an inquisitive mind is oftentimes where it starts, and dedication to trying to answer, unsolved questions and questions about our surroundings. And then I think for, my area of geology, love of the outdoors, willingness to travel and have some adventure is a big part of it. I would say get some job experience in the field as early and as quickly as you can. That way you can really decide what specific area you really want to pursue, and you'll also make some connections in the field that can maybe help you through your college years or even after in getting a job.
I could add to that too, that I think it's really important to hone your skills in the areas of mathematics and especially technology. If you have any interest in computer science, a lot of even the life sciences are so dependent now on those very technical skills. So I think if you can build those technical skills, that will always be something that will be a well sought after talent. Well, Greg and I were talking about this earlier and talking about some investigation that we've done on the Bureau of Labor Statistics. And the STEM fields are increasing in demand by 10% every year here in the United States. That means that as we go forward, that's going to be the greatest area of opportunity for students, is in those STEM fields. I think that's very important. And also the salaries are going to be very competitive in STEM fields.
Got a lot of areas on both the life and physical science side that with a little bit of experience very quickly gets into the six figures and has really good job security. We are needing these skills in our society. We are needing these skills in our industries. And quite frankly, we're not meeting the demands. We need more students to step up and follow these paths to fit the needs.
Certainly in the past, historically, STEM fields have been dominated by males, but there's been a lot of push to include females in those technical fields. And I think that we're seeing that gap kind of be decreased more and more as time goes on. And there certainly seems to be a lot of women in those STEM fields now.
It's hard to talk about sciences without doing some demonstrations. So I brought with me today some items that would allow us to experiment with electricity. So the first item I have is a Tesla coil. And the Tesla coil, when hooked up to an electric source, and when you hit the button, you hear a little bit of a buzz there. And that buzz is the generation of electrons. So when we talk about really any area of the sciences, we always begin with the basic structure of the atom. So when we think about the Tesla coil, it is using a band and some friction inside the mechanism to cause friction to generate electrons. And as we get a little bit more into the significance of electrons in the Tesla coil, we might look at a few light bulbs here. And the first item that I have is just a real simple fluorescent tube. And if I bring the Tesla coil over to that fluorescent tube, you can see that I get a couple things. First, I get a little bit of a lightning bolt jump from the Tesla coil to the fluorescent tube. And then of course the other effect is we see that we get some light coming off the fluorescent tube. So there must be some connection between electrons and electricity. That if we're generating electrons on the tip of our Tesla coil, and we apply that to a light bulb, we must then have a connection between electrons and electricity. So we can go quite a bit further with this, thinking about different conductors. You know, I have a basic piece of wood here where I might try to connect this fluorescent bulb with that piece of wood. And when I hit that wood with the Tesla coil and the electrons, I get no effect. So I know that wood is an insulator and doesn't really allow for the movement of those electrons. But if I switch that up a little bit and I put a copper piece of tubing here in place of that metal, you can see that I get the light from that fluorescent tube. So I get electrons that transfer throughout the material, which would of course make it a conductor. So we can think of this in many kind of ways. You know, the wood and the copper are kind of some classic examples of a insulator and a conductor. But something that's a little bit fun to experiment with is the conductivity of the human body, the conductivity of we could say myself here. So Carrie's going to step in and help me a little with this. I'll put the Tesla coil down. And this might seem like it is going to shock me, the process of this. But as long as Carrie and I do this right, as long as she does not generate the electrons when I haven't made contact with the Tesla coil, then I won't get shocked. Those electrons will simply move throughout my body. So I'll put the fluorescent tube in my mouth, and when I nod my head, we can turn the Tesla coil on, and when I shake my head, we can turn it off. This is her opportunity to get revenge of many years teaching together. So we can see there that my body is capable of conducting that electric current. I am capable of those electrons moving throughout me, similar to what we saw with the copper. So when we think about conductivity, we could extend this a little bit to solutions, to liquids, and what type of conductivity we have with solutions. So if we transition to over here in the experiment I have with this light bulb, we see that the light bulb is not lit up, and it is connected to an electric source. But the problem is these two prongs that extend down from the light bulb need to be connected with some type of conductor. So since these prongs are separated, the light bulb is not lighting up. But if I would, not going to, but if I would put this copper wire across both of those prongs, it would light up the bulb and also send a little bit shock to me, and I'll avoid that. But let's think about water. And what I have in this beaker here is some distilled water, some deionized water. So water in its very pure form. And if I lower the light bulb into that water, we can see if we get an effect of any light coming off the bulb. And you can see that we're really not getting any light at all off that bulb. So that must mean that water in its pure form is not an effective conductor of electricity. But there is something I could add to this water. I could add a little bit of salt and see what effect I might get on the addition of what we would call an ionized solution to the water. So I'll go ahead and add that salt. A lot of our salt over in the science lab has not had much activity the last few months, right, Carrie? There, that should be plenty, I would think. And then as I even stir it up, even before stirring it up a little bit, you start to see the light coming off of the bulb. So what I've created here is a solution that is capable of conducting electric current, and that is known as an electrolyte solution. So an electrolyte solution, a solution that is capable of conducting electric current. And this very much relates to its charge. So salt is sodium chloride. It is a charged substance, and that charged nature of the substance allows for the conductivity of the electric current. So these are just a couple experiments that are on that side of electricity, which is more on the physical science side. But again, no matter what area of science you go into, you begin your understanding, you begin your study with studies of the atom, which connected closely here.
Since we're hopefully nearing the end of the coronavirus pandemic, just one of the many pandemics that humans have had to deal with throughout history, it's a good time to talk about microbiology, so that's what I wanted to concentrate on today. Did you know that in the late and mid 1800s, people had no idea what caused disease? They thought diseases were caused by either bad behavior or some sin that a person had committed, or poverty, or maybe who you were related to. Now we know that disease is typically caused by tiny particles that are unseen. And you can imagine that in the 1800s, that was hard for people to accept. A man named Robert Koch and Louis Pasteur, and it is Louis Pasteur, that's the guy that came up with the process of pasteurization that makes milk safe and keeps it from spoiling very quickly in your refrigerator. But those two men came up what is known as the germ theory of disease. And so that germ theory has been very important for us whenever it comes to public health going forward. So have you ever had a wart? A lot of people have had a wart, or at least one or two in their lives. But it's interesting that throughout history, people didn't know what even caused a wart. And we know now that warts are actually caused by a virus. That virus is the human papilloma virus. And papilloma virus is one that's very interesting to talk about because it is actually a virus that causes cancer. It causes cervical cancer and other cancers. And it's also the first cancer that we have a vaccine for. So yeah, we have a vaccine that actually prevents several types of cancer. And all of that has come from the field of microbiology. Microbiology is an incredible field. Not only do you have virology that I've been talking about that concerns things like colds and flu, and then also coronavirus, but you also have the fields of immunology and biotechnology, microbial forensics, which is really interesting too. If you remember in 2001, whenever anthrax spores were mailed through the US mail, they were able to actually track down who came up with that strain of anthrax, who was growing that strain of anthrax, and figure out who the culprit was using microbial forensics. So this is a great field. Also in this field right now, there's a neat project going on called the Human Microbiome Project. Our bodies are colonized by microbes, and so many of these microbes that actually they outnumber our cells 10 to 1. And what we're finding out is that they have a huge impact on our health and well-being. And most of these microbes have not been identified or characterized. So one of the things that my students do in my microbiology labs is they start to study not only just microbes that are found in the environment, but also these microbes that colonize our bodies. And I have some culture plates that I brought to show. So the first example that I have is an example that my students take whenever they first come into the micro lab. I have them use the restroom and then come back from the restroom without washing their hands. They swab their hands, and then we look at what types of microbes they might have picked up while they're in the restroom. And we have some microbes here on some different types of media. This is McConkey agar, and the particular example that we see here, this light pink color, is typical of E. coli bacteria. And E. coli also, on this type of medium, which is known as EMB, produces a really interesting green metallic sheen. So that way students can see just how common these bacteria are in the environment. The term that we use is ubiquitous, meaning that we find them just everywhere in the environment. I also have an example, and this is another example of microbes that live in and on our bodies, and which is part of our what we call the microbiome, the human microbiome. But I have an example of 2 swabs, nasal swabs, taken from 2 people that live in the same household, but they're growing very different bacteria. Both of the bacteria are a type of bacteria that you probably heard of called Staphylococcus, and we always tend to think of the staph that causes infection, which is Staphylococcus aureus. Some people are colonized with Staphylococcus aureus, and some people are colonized what is considered the normal type of bacteria, which is Staphylococcus epidermidis. But they're cousins, they're kind of in the same family. So if we look at this first plate, this one, where you see there's no change in the color of the agar, is the one that comes from a person who is characterized with what we would call normal flora, or Staphylococcus epidermidis, the non-pathogenic form of staph. But if we look at this other plate, this one is actually colonized with Staphylococcus aureus. So these 2 people, like I said, live in the same household, and yet they are colonized with 2 different bacteria. This is the one that whenever you hear staph infections, it's referring to Staphylococcus aureus. So, and if you are very familiar with medicine and antimicrobial resistance, that's a huge problem in medicine right now. A lot of our antibiotics no longer work as well as they used to, and that's because these bacteria have evolved to have different mechanisms for avoiding being destroyed by antibiotics. I also have a neat example here of a type of bacterium that's one of my favorites. It's called Serratia Marcescens. It's known as the bloody bacteria. And the reason that it's known as the bloody bacteria is because this particular bacterium turns red whenever it's grown at room temperature. So I have 2 examples that I grew in the lab. The first one is Serratia Marcescens right here, that was grown at 37 degrees, which is what our typical incubator temperature would be, or that's what body temperature is. And as you can see, it's just a kind of a pale color, not very interesting. But then whenever we look at the same bacteria and we grow it at 25 degrees Celsius or closer to room temperature, you can see that it's red. And that's due to gene regulation. There's a gene that produces that red pigment that's only turned on at lower temperatures. This particular bacteria has some interesting history too, because Alexander the Great, whenever he was considering attacking the city of Tyre, was very concerned about whether or not this would be a successful campaign. And so he and his soldiers prayed to the Greek gods and asked for some direction as to whether or not they should attack the city. The next morning when they got up, their bread was red. And it's suspected that that is because it was contaminated with this particular bacterium, Serratia Marcescens. So microbiology is a fantastic field. The interest in microbiology has just exploded, especially with the current situation with the coronavirus pandemic. It is a field that is the field where vaccine development takes place. It is a field that is exploring all of these microbes that live in and on our bodies and probably affect our health. If you're not interested in computers or math, but you're still interested in science, this is a good direction for you to go. Incidentally, I'll tell you another little story about human papilloma virus that I was discussing earlier. The virus that we actually have a vaccine to prevent the cancer that comes from that virus. That virus was discovered by a man named Richard Shope, and he was hunting in Iowa. And as he was out walking in the fields, he noticed a bunch of cottontail rabbits that had what looked like horns. And so being a person who was a very inquiring and investigative type person, he captured a bunch of these rabbits and took them back to his lab and did some experimentation on them. And he discovered that not only do humans get papillomavirus, but rabbits do as well. And so these things that looked like horns were actually cancerous growths that were essentially large warts. And if you have made the connection already, which you may have, these are the source of the jackalope myth. And so those viruses actually caused those funny horn-like growths on the rabbits. So it's an interesting field, and I think a field that a lot of people come into, at least my labs, and they're not really excited about taking a microbiology class, but after being there and spending some time in the lab, they find that they really enjoy it.
If you're interested in a career in STEM, Rend College is here to help you prepare with a variety of programs to develop the knowledge and skills needed. RLC has transfer degree programs such as Biological Science Associate of Science degree, Chemistry Associate of Science degree, Associate of Engineering Science degree, Engineering Technology Associate of Science degree, Industrial Technology Associate of Science degree, Mathematics Associate of Arts degree.